Okay, Assalamualaikum and very good morning.
Good morning, doctor.
Good morning.
Okay, so it's already 11:04. Let's start our class today. Okay, so for today we are going to discuss and continue what we have started 2 weeks ago for the class. Okay. Before I continue with the second part, typical mature response, I'd like to first of all to recall the things that we have discussed in our last sessions. Okay. And I'm hoping that you will understand better now and then remember the basic concept before we go to some basic material responses that you may encounter when you deal with various types of materials. And then after that, this will be a short session for lecture 2. And then we are going to continue with the lecture 3, where we are going to look at the thermodynamics of deformations. This is important, especially later when we want to derive mathematical equations to describe the mechanical response of materials. Then there are certain theoretical framework that we have to respect. And then thermodynamics provide us with that guidance on the restrictions of how we can develop a materials model. Okay, so combined between this lecture, end of this lecture 2 and then lecture 3, it will be, I believe, a shorter sessions than we used to have in lecture. And starting from next week, we are going to start by lecture 4, which deals with the first class of material response that we are going to discuss in this lecture, which is linear elastic material response. Okay. Before that, let's look back on what we have seen 2 weeks ago. Okay, don't forget to scan your the QR code for your attendance. Okay, few remarks that we have seen 2 weeks ago is that we have learned about mechanical properties of materials. So these are the things actually that you have seen in the first year when you learn about material science and engineering. Okay, we have seen that the easiest way to obtain the mechanical properties are by conducting tensile tests. Okay? With the tensile test, you can obtain the stress-strain curve. From the stress-strain curve, then you can extract a number of mechanical properties, such as elastic modulus or modulus of elasticity or Young modulus, and then yield strength, tensile strength, ductility, toughness, and so on. So we have seen that, all right? So these are the standard when you want to evaluate the mechanical properties. However, in many cases, this is not sufficient, especially when you want to use it for design purpose, for components made of certain specific materials under complex loading conditions. Because in reality, materials in applications where load-bearing capacity are important, the mechanical loading is usually complex, okay? And then this cannot be captured by the simple tensile test that we conduct to extract the mechanical properties. So we need to do other tests so that we will have more idea on the characteristics of the materials. We have seen last week that when we conduct tensile tests, we can do the tensile test by doing 2 different ways on how we control the machine. Okay, the first is by imposing displacement rate, or it is equivalent by imposing strain rate, and this is called as displacement rate or strain rate control. Okay, the idea here is that we fix the displacement rate, and then we see what will be the stress-strain curve of the materials during the test. So displacement rate is equivalent by imposing strain rate, in the sense that if you remember the equations for the strain, engineering strain here, it is delta L over L0, L minus L0 over L0. The rate of the strain is simply the rate of length, the change of length, which is the displacement rate, over initial length. So if you impose the displacement rate, L dot here, the unit will be millimeter per minute, millimeter per second, right? It depends, but it is length over time. If we divide it by the initial length of your samples during the test, then you get the strain rate. So the unit of the strain rate is 1/second, for instance, 1/minute, for instance. Okay. So we impose either constant displacement rate or constant strain rate, and then we observe what happens to the stress strain curve of the materials. The second way is, we have seen 2 weeks ago, is by imposing force rate, how fast the load that we want to impose, which is equivalent by imposing stress rate. And this is called as force rate or stress rate control. Okay, so because the stress to the force is simply related to these simple equations, so the rate of stress is simply the rate of force divided by the initial cross sections of your sample that you want to test. Okay, which means that in this kind of control mode, you impose during the tensile test constant force or constant stress, and then we observe what happens to the stress strain curve of the materials. We have seen this example 2 weeks ago. This is highlighting that two different choices may give you two different stress strain curve. And then by looking at the result, then you can learn, if I want to understand certain characteristic of materials, what types of control mode that I can choose, that I should choose. Is it displacement rate control or force rate control, as given in this example? Okay. So we have this in the last 2 weeks. 2 weeks ago, we learned about, we have a metal, for instance. The properties are given, yield strength and tensile strength. So two samples, one is subjected to loading 1. The other sample is subjected to loading 2. So loading 1 is force control. So we impose force. In loading number two, it is displacement control. Okay, so you impose displacement as a function of time. The two simply means that you load the materials and then you remove the load from the materials. The only difference is that the types of load, loading 1, it is force you impose, loading 2, it is displacement that you impose. So in the first loading types, the materials is initially at 0 force. You pull it by certain amount of force up to the maximum at point A here, 30 kilonewtons. After that, you bring the materials to point B where the load is 0, where the force is 0. Starting from 0 force to 30 kilonewton force and bring back to 0 force. The second loading is slightly different, even though it is the same in the sense that it is loading and unloading. So it starts by 0 displacement, and then you extend the material such that the length increases by 1 mm. And then after that, you bring back to the initial length, so 0 displacement. It is different, okay? So what we expect the stress strain curve, we have discussed it last 2 weeks, okay? So for loading 1, what we need is that we need to check first what is the stress level at point A. If the stress level in point A is higher than the yield strength, then plastic deformations occur. If it is lower, then plastic deformation will not occur. So we check it, we have seen it is higher than the yield strength. So point A is already beyond the initial yield strength. So when I return back from A to B, it means that I need to bring back the materials to 0 stress. 0 force means 0 stress. And this is what we will get. Okay, so it starts from point O here, 0 load, 0 force, 0 stress. Bring to point A, so this is the yield strength. So you will exceed the yield strength to the point A, okay? And then it is higher than the yield strength, so plastic deformation will occur. So when you unload, you remove the load, so it will bring back to 0 force or 0 stress. But it will not going back to the initial path here because you introduce plastic deformations. So instead, it will follow this curve to point B with the same slope. Okay. So point B, as you can see here, is zero force, zero stress. But it does not necessarily mean that it is zero strain. So when you remove the force, you remove the stress, the materials will undergo certain amount of permanent deformations. The length of the sample will change permanently. Okay, so again, point B is zero force, zero stress, but it does not mean zero strain. For loading number 2, this time we impose displacement. Okay, so we bring from point O, we extend it by 1 mm, and then after that, we bring back the materials to zero displacement, zero strain. So it is different with the first case. Okay, so similarly here, we need also to identify whether at point A, we already exceed the yield strength or not yet, whether plastic deformations occur or not yet. So we can determine what is actually the strain at yield, which is the sigma yield over elastic modulus, which is 0.001. And this is way lower than the strain at A, which is 1%. So which means that at point A, also plastic deformations already occur. All right. So in these situations, we have to bring back, if I go back here, after point A, we have plastic deformations. Okay. And then when I bring to the point B, I need to bring the sample to zero strain, zero displacement, not zero stress, which means that after it is at point A, I need to bring back to zero strain, which means that the point B will be located at the vertical axis. Okay, where more precisely vertical axis? Now, here's the thing. It depends on the characteristic of metal. Because we deform plastically the materials, a phenomenon, the strengthening phenomenon, occurs something which is called as strain hardening. You have learned it in material science. Okay, so the fact that here you load the material to the stress level at point A, you deform it plastically, you increase the strength of materials. Okay, when you increase the strength of materials, what is the consequences? The yield strength will increase. So the initial yield strength is this one. Because you already load to the stress level higher than the yield strength, so here becomes the new yield strength of the material. So as if the strength of materials is improved, this is strain hardening. Okay, so you have increase in the yield strength from sigma yield to become sigma A. Sigma A is the maximum stress attained during the test. Now, this is the improvement of the strength in tensile. What happened with the yield strength in compressions? Because materials has yield strength in tensile and also yield strength in compressions. So you may have two different cases, extreme cases. The first extreme cases is that when you increase the yield strength in tensile by certain amount, you will also increase the yield strength in compressions by the same amount. And this is called as isotropic hardening. So if initial yield strength in tensile is sigma yield, sigma y here, and the initial yield strength in compression is minus sigma y, then because you deform it plastically, the materials undergo strain hardening, the new yield strength in tensile becomes sigma A, the new yield strength in compressions becomes minus sigma A. If you deal with this kind of response, if you find this kind of stress strain curve, then your metals experience a types of hardening which is called as isotropic hardening. You gain certain amount in tensile, you gain also the same amount in compressions. This is why it is called isotropic. Okay, so now the materials will change its properties. The yield strength will evolve from sigma y to become sigma A in tensile to become minus sigma A in compressions. Okay, this is how we modify the properties of materials, the strength of materials, which is by, in this example, is strength hardening. In the second extreme case, is that when you earn increase in the yield strength in tensile from sigma y to become sigma A, what happened? For instance, the change from sigma y to sigma A is by the amount of delta sigma. What happened for the yield strength in compressions? You lose by the same amount. So it is unlike in the case of isotropic hardening. You gain in tensile, you gain in compression. That is isotropic hardening. In the second case here, you earn in tensile, you lose in compression by certain amount, the same certain amount. So here, the new yield strength in tensile become sigma A, and the new yield strength in compressions become minus sigma Y minus this amount. So it is here. So the amount of yield strength in compressions is reduced. The amount of yield strength in tensile increases by the amount of delta sigma. The yield strength in compressions reduces by the same amount delta sigma. That's what happened. In the second extreme cases, it is called as kinematic hardening. Okay, so if you look at and you get this kind of curve, then your metals undergo what is called as kinematic hardening. Okay, so if we look at point B here, as you can see, the displacement is 0, the strain is 0. The point B here, the strain is also 0, but the stress is not 0. Similarly, in the case of isotropic hardening, the point B here, the strain is 0, but the stress is not 0. Okay, so this is how different the response that you get by imposing different types of loading. If you want to know the characteristic of the strain hardening in materials, whether it is isotropic or kinematic hardening, then you need to do the tensile test by imposing a displacement control or strain rate control, which is loading number 2. Because if we go to loading number 1, the result that you will obtain is this one. You will not know whether the yield strength in compressions will evolve following isotropic hardening or kinematic hardening. Is there any question so far?
No, doctor.
Okay. The idea, okay, great. Again, I will repeat. The idea here is that you can modify the strength of metals by deform it plastically. Okay, if you deform it plastically, such that the stress, the yield strength increase in tensile. Okay, so you need to observe also whether the yield strength in compressions change, and if it change, how it change. Is it in the isotropic manner or is it kinematic manner? In many cases, it is combinations between isotropic and kinematic hardening. So what I explained here is 2 extreme situations. Okay. For practical purpose, simply saying that if you need metals which, for instance, require yield strength of 500 megapascal, but you only have metals with the yield strength of 400 megapascal. So what should you do? One of the simplest way is simply deform it plastically, stress it up to the stress level of 500. So once it is deformed plastically, what will happen is that the materials will undergo strain hardening, then you will obtain new yield strength, which is 500 megapascal. That is in the simple word. Okay, so you can modify the strength of materials. So this is to sum up the difference between isotropic hardening and kinematic hardening. So I put both here. So here in the case of isotropic hardening, the elastic regions expand symmetrically. symmetric because the increase here, if you look at this axis, the increase in tensile is followed by the increase in compression by the same amount. So it expands symmetrically. While in kinematic hardening, you keep the same size, but it is moved up and down. Okay, if the yield strength in tensile increases by delta sigma, then the yield strength in compression reduced by delta sigma. Okay, so the distance between the new yield strength in tensile and the new yield strength in compression remains the same as in the initial state. So the consequence of isotropic hardening is that any increase of yield strength in tensile is followed by the same amount of increase of yield strength in compressions. In the case of kinematic hardening, any increase of yield strength in tensile is followed by the same amount of decrease. So it's opposite of yield strength in compressions and vice versa. Okay, this is especially important when you work in metal forming industry, when you have to deform plastically the materials, and then these materials will be used to certain applications, especially if the applications involve compressive stress. Be careful. You need to check after you do the forming. For instance, forging. When you forge the materials, you need to press it. Okay. Or you need to pull it until it undergoes plastic deformations. You need to be careful to check what are the new yield strength in tensile and in compressions, and whether it is still suitable for the applications that you would like to use. So again, this is another explanation so that you will have a more idea about isotropic hardening and kinematic hardening, because this is the simplest way how you can modify the strength of metals. Okay, so here, if for instance, again, I explained this is the tensile stress strain curve of metals under tensile test. Let's say that I do the same test but by compression. So this is the stress strain curve. This is the yield strength in tensile sigma y0. This is the initial yield strength in compressions minus sigma y0. So what we have here is that if we stress the materials to the stress level between sigma yield 0 and minus sigma yield 0, then the deformation will remain elastic. Your stress level does not exceed the initial elastic domain. So this is called as initial elastic domain. If you stress the materials in tensile or in compressions inside this elastic domain, then you will not induce any plastic deformations to the materials. Okay. Once you impose stress higher than the initial yield strength, for instance, if you put it here, you alter the microstructure, you deform it plastically. So the yield strength of materials will change and now to become sigma yield 1, which is this one. In the case of isotropic hardening, then the yield strength in compressions will change from minus sigma y0 to become minus sigma y1. So it remains symmetric. You have increase of the yield strength in tensile, you have also increase of the yield strength in compression by the same amount. So which means that now the elastic domain evolved. Initially, this is the elastic domain between sigma yield 0 to minus sigma yield 0. Now the new elastic domain become from sigma yield 1 to minus sigma yield 1. So after this test, if you use these metals after deforming plastically, then the yield strength become in tensile sigma y1, in compressions minus sigma y1. So when you use it in application, if you stress it at the stress level higher than sigma y0 but lower than sigma y1, then your metal will deform elastically because you already alter the properties. Okay. So this is why the elastic region is called to expand symmetrically, because increase here by delta sigma, it is also increased here in compression delta sigma. So the elastic domain expand symmetrically. In the case of kinematic hardening, so here the difference is that you gain the yield strength in tensile by delta sigma. Here, if the initial yield strength in compression is minus sigma yield 0, then it is reduced by the same amount delta sigma. then this become the new yield strength in compressions. So when you compress it here, so here becomes the new yield strength in compressions. So which means that the elastic domain, which is initially between sigma yield 0 to minus sigma yield 0, now move between sigma yield 1 to sigma cy1. The size of the elastic domain remains the same. Okay, so this is called as the elastic regions move at constant size. So initially it is here to here, the new one become here to this one by maintaining its size. Okay, so this is just a comparisons between the two. Any questions so far? Is there any question so far?
No, Doctor.
Okay. So see it from the engineering practice perspective, mechanical engineering, that you can modify the strength of materials, especially metals. Just deform it plastically, then you alter the strength. You increase the strength. Okay. So if you look at in the table, in the books, in the handbooks of certain yield strength of materials, it is the initial yield strength, which is a property. But you can alter it, you can modify it, for instance, by deforming plastically. Okay, this is called as strain hardening. Okay, now, so these are the things that we have seen last week. Okay, hopefully it is clearer for you now. So in the next few slides, for closing this lecture number 2, I'm going to browse the typical mechanical response of materials that you can get. Okay, how different materials may have different stress strain curve. Not only by conducting tensile tests after fracture, but to do something slightly different than that. It is by similar to the example that we have seen before, where we impose loading and unloading. We impose load and we remove load, and then from that you will see that different materials could show different stress strain response. Okay, so the first one here is that now I'm focusing by imposing the load during the tensile test in the form of force control or stress control. Okay, which means that now this is F, force, as a function of time. So what I do to the materials during tensile test is that I pull it up to certain maximum force, and then I bring back to zero force, zero stress. So it is loading number 1 in the previous example. If you observe the response of the materials stress strain curve, and this is the curve that you have. This is during the loading. By saying loading, it means that from 0 here, loading or uploading, it is the same meaning. I use it 2 words for the same meaning. And then when we go down, it is called as unloading. Okay, so if it is loading go up here and unloading following exactly the same line there, and then it is a line, there is no curve, then it is called as linear elastic material response. Okay, so what do we observe here is that after we bring to maximum force and then remove the force, the materials returns to initial point, initial zero strain, zero stress. It means that there is no permanent deformation. There is no plastic deformation. The deformation is entirely elastic. And then if we see the stress strain curve, it is a line. That's a simply straight line. So which means that there is linear relationship between stress and strain. It is proportional. If you double the strain, then you double also the stress. Okay, and then from thermodynamic standpoint, it is reversible process. So you deform the materials, and after that, it returns to its initial shape. So it is a reversible process. And then actually, it is time and rate independent, which means that if you pull the sample slowly, or you pull the sample relatively fast, but you still get the same stress strain curve, then this is the typical linear elastic material response. So this is the simplest response. Okay, and then typically you will find linear elastic material response for metals if you load it to the stress level below the yield strength. So different types of metals, even different types of polymer, different types of ceramics, if you load it not exceeding certain critical level, then the deformation is elastic and it is linear elastic. Okay, so again, typical metals at room temperature bring at the stress level below the yield strength, then you get this linear elastic material response. Okay. The next material response is something that you will obtain as shown in this figure. Yeah, we impose the same load during the tensile test by controlling the force, loading to the maximum force, and then unloading, bring back to zero force here. And then if you observe the stress strain curve, and then if you observe something similar like previously, except that it is now a curve. It's not a straight line. Okay, which means that the function, the curve here is non-linear. Okay, some observation that we found here is that it is during the loading up here, unloading, coming back to the initial point. So the deformation is non-permanent. The deformation is still elastic. The only difference with the previous response is that it is no longer a straight line. It is a curve. It is non-linear relationship between stress and strain. Okay. And then again from the thermodynamic, because you recover the initial length, there is no plastic deformations, then it is a reversible process. Also, if you do the test one by imposing force fastly at the fast rate, and another one is relatively slow rate, and you still have the same curve, it means that it does not depend on the time, it does not depend on the rate. It is called as time and rate independent. You only have one curve here. And this kind of response is called as nonlinear elastic material response, or typically called also as hyperelastic. The material which show these kinds of response are typically rubber materials, especially with low amount of filler. Okay. Vulcanized rubber with low amount of filler usually show this nonlinear elastic material response. Okay. The next one is something that you know well. We have discussed before. If I impose load and this is the typical stress strain response that I have, it means that it is elastoplastic material response. Why I said elasto and then plastic? Because for any plasticity, there is always certain part of elastic deformations. Okay, so the characteristic of this kind of material response is that the deformation is permanent. There is plastic deformations because the stress level is higher than the yield strength. You bring the materials to the stress level higher than the yield strength. And then initially it is linear here. Before then you start to have curving after you exceed the yield strength. From the thermodynamic standpoint, it is irreversible process because the deformation is not recovered entirely. Okay, you have plastic deformation, you have permanent deformation, so it is irreversible process. And then also, it is characterized by the fact that the stress strain curve is independent on how fast you conduct the test. Okay, it is called as time and rate independent. So typically, it is metals. We find it in metals at room temperature, at low temperature, loaded to the stress level higher than the yield strength. And then the next one is you may have something like this stress strain curve. Okay, when you impose uploading here, so this is the curve, something similar like nonlinear elasticity. But when you unload, you remove the force. Okay, what happened is that here it does not follow the same path. Instead, it is another path. And then sometime here, most of the time it is here, you're going back to the zero strain. Okay, so what this kind of stress strain curve can be characterized by certain aspect here. First is that typically it is non-permanent deformation. Your material seems like it still returned to its initial shape. It returned to its initial shape. Okay. If you look at the stress strain curve, it is non-linear. Okay. From the thermodynamic standpoint, even though you bring back to the initial length, the initial deformations, the deformation is recovered, is non-permanent. However, there are certain processes occur in the materials which is irreversible process. Okay, and this is characterized by the area between the uploading curve to downloading curve, which is hysteresis. Okay, it is the amount of energy dissipated during the loading and unloading. Okay, it is irreversible process from the thermodynamic standpoint. It is dissipative process. And then you will find also that the stress strain curve depend on how fast you do the test. Okay, so the size of the hysteresis loop will depend on whether you do the test fast or you do the test very slow. Typically, if you do the test relatively fast, then the hysteresis loop will be larger. If you do the test at relatively low rate, then the stress strain curve becomes smaller. So this is the typical response of the materials, which is called as viscoelastic material response. And you can find it in certain types of materials, such as polymer, especially also you can find it in rubber, which is filled, reinforced by a filler, typically is carbon black. So it will have a response similar to this one, viscoelastic response. The stress strain curve depends on how fast you load it. Okay. So the next one is called as viscoplastic material response. What does it mean? It is similar to plasticity, except that the stress strain curve is depending on how fast you load the materials. So if you load relatively slow, you have one stress strain curve. If you load it at faster rate, you have another stress strain curve. So usually the yield strength is affected by how fast you load the materials. And this is called as viscoplastic material response. You will find this kind of response in metals at relatively high temperature. For instance, when you deal with the chamber, combustion chamber, okay, the metals that use as a combustion chamber, it is operating at high temperature. Then when you design it, when you do stress analysis, you need to make sure that you take into consideration viscoplastic response. If you are designing, for instance, solder materials for electronic packaging or for chip, for instance, the solder materials are viscoplastic materials. Okay, so when you design it, so you want to evaluate the reliability of your chip in your mobile phone, for instance, when you want to design it, then you need to make sure that you take into consideration viscoplastic material response. Okay, so basically, these are the things that I'd like to discuss for the lecture 2. So we have seen basic mechanical properties. So recalling few notions of mechanical properties so that we agree on the definitions, we understand it, we remind what we learned before so that we will use it easily in the next lecture. And then also a few material responses that we have seen characterized by different shape of stress strain curve for a given loading mode that we can do during the test. Okay, so I will stop here for the lecture 2 before moving to lecture 3. Before that, if there is any questions, please let me know. Is there any questions so far?
Sir, I want to ask a question.
Sure.
For a same strain rate, can the same strain rate have different force? I mean stress rate.
Difference. Okay, that's a good question. Okay, there is a good question. Where you are comparing between two different loading mode, right? Loading 1 and loading 2. Loading 1 is strain rate. Loading 2 is stress rate, right?
Yeah. My question is like, okay, can one material have same strain rate but have different stress rate?
Of course, especially if it is non-linear, because you see that if the stress if you pull it, if your material is linear elastic, it is only a line. So if you pull it, for instance, you impose strain rate, certain strain rate, and then you will get more or less the same rate for the stress. But if it is non-linear, then it will be different. There's when the material's response becomes more complicated. Yeah, is that answering your questions?
I see. Thank you.
If it is not clear yet, please ask again questions so that I can elaborate more. Yeah. So it depends on the material itself. So yes, it can be different, of course. The increase in the strain and the increase in the stress, if the material response is linear, then it is the two are constant, it's the same. Okay, but it's not the same. It's proportional, I would say, by certain factors. But if it is non-linear, then there is no constant relationship between strain rate and stress rate.
Okay, thank you.
Okay, clear, yeah? If it is still not clear, let me know. Any other questions?
Sir, I have a question, sir. Hello.
Yes, please go ahead.
So regarding the isotropic hardening and kinematic hardening,
Okay.
so strain hardening occurs between the yield strength and UTS, right, sir?
I would say it start to happen starting when we exceed the initial yield strength.
So my question is, after if, for example, the stress passes the ultimate tensile strength,
Right.
does kinematic hardening and isotropic hardening still can occur or not?
Okay, good questions. The hardening still occur. Okay, it's continuously. The more plastic deformations that you have, the more strengthening mechanism that you will have. And then if you recall what you learned in material science in year 1 is that what happened when you deform plastically the materials is that you produce more dislocations. When you produce more dislocations, the density of dislocation increases. If the density of dislocations increases, the dislocations cannot move easily anymore. The fact that the dislocation cannot move easily anymore, this is what we see macroscopically as the increase in the strength. So yes, it will continue. The thing is that why we see in the stress strain curve after the tensile strength it goes down, it is because the load bearing capacity of the materials will reduce. Okay, so the stress strain curve is defined by engineering stress. Engineering stress is force per initial cross section. The initial cross section is constant. So when you reach the peak, after that, the load bearing capacity reduced because the cross section reduced significantly due to necking. So it goes down as if it gets weaker, but actually it is not. It's continued to go up. It continued to get stronger. So it is not only between initial yield strength to tensile strength, but all the way until the materials get fractured.
Okay, sir.
Is that answering your questions, Ravi?
Yes.
Okay, good.
My name is Deepan Raj, sir.
Deepan Raj, yeah? Okay.
Okay.
Sorry, okay, Deepan Raj. Okay. Any other questions? I hope this is clear, yeah, as a basic fundamental of materials, yeah, the idea. So you can alter the strength by deforming plastically. Okay, clear? No other questions before I start with this lecture 3. Okay. This lecture 3 deals with the thermodynamics of deformations. Okay. Again, as I mentioned in the early of the sessions this morning, is that our objective is to learn how we describe mathematically the various material response that we have learned just now. So linear elasticity, nonlinear elasticity, viscoelasticity, and then viscoplasticity. Okay, so each of these material response required different mathematical equations to describe the stress-strain relationship. materials model. Okay, how can we learn to develop or to create a mathematical models to describe the stress strain curve? Can we do it arbitrarily? Well, the answer is no. There is certain restrictions. There is certain guidance. There is a framework that we have to respect. And this framework is given by the thermodynamics, especially dealing, in our case, is thermodynamic of deformations. So this is probably where you learn that the thermodynamics that you have learned and the mechanics of materials that you learn has a strong relationship between the two. Okay, how actually the stress strain characteristic of materials, describing the stress strain response of materials, is guided by the fundamentals of thermodynamics, especially the thermodynamic of deformations. Okay. You will learn here two different types of elasticity, as you will see later. One is called as energetic elasticity. The other one is entropic elasticity. We will see what are the difference between the two, which materials are energetic elasticity, which materials are entropic elasticity. Okay, so this is the background of this. Another basic foundations before we start in lecture 2 dealing with linear elastic material response. So as I mentioned, we are in lecture 3. So next week we start by learning how we develop constitutive model or constitutive equations or materials model for linear elastic material response. Okay. So here to start the discussions. How actually we can derive a materials model. So I will use different terms for the same meaning. Okay, material model, constitutive model, constitutive equations. These are the same thing here in this lecture, which refer to the equations to describe stress and strain. Okay, so actually there are two ways how we can derive a materials model. First is what is called as using physical approach. The second one is called as phenomenological approach. The first approach is often used molecular theory. The second approach uses continuum theory. Okay, what does it mean? In the simple word, in the first approach, if we want to describe mathematically the stress strain response of materials, we need to understand the molecular structure of materials. Means that we need to go into the microstructure, see what happened during the deformations of the materials, and then from that, extract the informations, translate it into mathematical equations relating stress to strain. This is called as physical approach using molecular theory. It is molecular theory because you need to look at the molecular structure of materials. The second approach is, the idea is simpler. I don't want to know the molecular structure because it is too complex for me. The idea is simply, I need to describe correctly the stress strain behavior of materials so that I can do a proper design of materials. Okay, and this is using continuum theory. So the idea is that I don't need to look at the microstructure in detail. What I need is just simply come up with the proper mathematical equations which describe well the stress strain characteristic of materials so that it helps me in design. That's the whole idea. So we will learn both in this lecture. Okay, see how the difference between the two in more detail. If you have any questions, you can always interrupt me or you can type in the chat box. Yeah. So here are some detailed differences between the two. Physical approach, phenomenological approach. So in physical approach, describing the macroscopic nature of materials, in this case, we are dealing with the stress strain characteristic by a direct considerations of the molecular structure of materials. So we look at the microstructure. In the phenomenological approach is that we need to describe the macroscopic nature of materials, the stress strain characteristic, but without the need to directly involve detailed knowledge of materials molecular structure, as I mentioned. Okay, so what will be the consequence of these two different philosophy? Here, If you are using physical approach because you consider the molecular structure of materials, the mathematical equation describing stress and strain is usually complex mathematical equations. And the mathematical equations will involve parameters, will involve constants. The constants have physical meaning. It can be directly linked or related to physical structure of material. So it is something physical. Your mathematical equations will be more complicated, but it involves certain parameters which are physical in nature. It has certain meaning. So it is easy for you to understand because the parameters represent something physical in the materials, but relatively complex mathematical expressions. When we use the second approach, from mathematical standpoint, it will be simpler expressions. And again, of course, it will involve parameters, but since we do not link directly to the microstructure, then the parameters that you have will not have any physical meaning. It is just simply there. It is just a simple mathematical equations without any specific physical meaning, as long as you can describe well the stress strain characteristic of materials. So this is two different approach that people do in modeling of material. So as you can expect, physical approach usually is quite accurate in the sense that it gives you really something physical. But the limitation is that because the mathematical equation is very complex, so it is challenging if you want to deal the real case in design involving engineering, okay, complex structure, complex loading conditions. When it comes to phenomenological approach, it has advantages that you can deal with complex real engineering situations, but with certain limitation, lack of accuracy, for instance. Okay, so it comes with pros and cons for a different approach. So now, whatever approach that we will use, whatever method that we use, we always need to refer to thermodynamics because it gives us general framework and restrictions. What can we have, what we cannot have in our mathematical model. Okay, so there is the reasons why we are going to look at the thermodynamics of deformations. So we apply thermodynamics to solid materials under elastic deformations. That's what we are going to do. Okay, we start by elastic deformations for simplicity. Again, think of materials or tensile specimen under deformations. And then we will look at how the thermodynamics see this process of deformations. Okay. So let me start by recalling the first law of thermodynamics. This is something that you have learned, you master well. The first law of thermodynamics you can express in different various ways, but the whole idea is that it relates to conservations of energy. Okay? If you are considering a certain medium, focusing on certain medium, which is called as a system, okay, the systems will have certain amount of energy, which is called as internal energy. Okay, so the internal energy of the materials of the system that you have, you can alter it, you can modify it, you can increase it, you can decrease it by either supplying or extracting energy in the form of heat or in the form of work. That's the whole idea. If you have a system with certain internal energy, then the internal energy will increase if you supply heat into it or if you supply work. It will decrease the internal energy if you extract energy in the form of heat or you extract energy in the form of work from the system. As simple as that, actually. So if I put it in mathematical notations and put the formal definitions of first law of thermodynamics like this, so the increase in the internal energy of the system, which I denote as du bar, the change, the increase, okay, is equal to the amount of energy added by heating the system plus the amount of energy as a result of the work done to the system, dW bar, or simply this one. Okay, so du, the change of internal energy, is simply the sum of the change of the heat that we supply or we extract plus the change of work that we supply or we extract from the system. If dq is negative, it means that we extract energy in the form of heat. If dw is negative, it means that we extract work from the systems outside. Okay, minus minus, so du become minus, it means that the internal energy will decrease. It's simple as that. So dq from the thermodynamic is simply T ds, or T is absolute temperature, ds is change of entropy. Okay. While dw is F times dl. F is the force that we apply to the materials to stretch it, times dl, the change of length, something to do with deformations of materials. Okay. Now, using this first law of thermodynamics combined with useful definitions of free energy, okay, in the next slide here, especially Helmholtz free energy, which represent, well, loosely speaking, is a portions of energy that can be converted into work. Okay. So if we focus, for instance, more specifically Helmholtz free energy, psi bar equal to internal energy minus Ts. So psi bar is energy, so the unit is joule. Internal energy is also energy, the unit is joule. Entropy S, the unit is joule per Kelvin, and the absolute temperature unit is Kelvin. Okay. So now, what we need is how much is the change of free energy during certain process. Okay, because we cannot measure the absolute amount. What we can identify is the change of energy, right? So it may looks like still very not clear here, but later we will see that it is useful for us to understand how the deformations of materials from the thermodynamic standpoint. So if I now look at the change of free energy, Helmholtz free energy, d psi. So I just apply a simple chain rule. So d psi is simply du minus the chain rule T ds s dt, as simple as that. This is a chain rule. Okay, and then if I use the first law of thermodynamics in the previous slide, where du is equal to dq plus f dl, okay, so this is dq plus f dl, dl here is equal to du minus tds minus sdt. From the first law of thermodynamics, it is also mentioned that dq is equal to tds, so they cancel out each other. So finally, I have this relationship here. The change of free energy is the sum of the change in the system related to the change of deformations and the change of temperature. So when we deform the materials, the free energy change. When we change the temperature of the materials, the free energy also change. So it is a functions of the change of length, which is deformation, and the functions of the change of temperature. Now, what happens if I focus on certain specific situations? Again, if it is not clear, if it is too theoretical and then you're lost, you stop me, you let me know. Okay. Now, what happens? What will be the change of the internal, the free energy in the case of constant temperature? So in this situation, we get this constitutive relation. First, we get force needed to stretch the materials and defined by the change of free energy with respect to the change of length at constant temperature. If we do at constant temperature, it means that dt equal to 0 here. So easily we can have F is d psi over dl. If we simply focus on the process of constant deformation, no deformations at all, so the change of free energy with respect to temperature at constant length gives you entropy. Okay, so these are the two constitutive equations that we get from combining the definitions of Helmholtz free energy and the first law of thermodynamics. So the force is simply the differentiation of free energy with respect to deformation. The entropy is simply the change of free energy with respect to the change of temperature at constant deformations. Now, since we are only focusing on the stress-strain response of material, so I will not talk about entropy temperature here. I will only talk about force elongations, right? I will only focus on the first constitutive equation here, which is the force. This is the force needed to deform the materials. So if I look at here, and then insert the value of free energy, which is given by U minus Ts, then at constant temperature, I have these equations. So the force needed is the change of the free energy at constant temperature equal to the change of internal energy with deformations at constant temperature minus T times the change of entropy with deformation at constant temperature. So the first term here related to internal energy. The second term here related to the change of entropy. So the first term is often called as energetic contributions of elasticity. The second term is often called as entropic contributions to the elasticity. So what does it mean, this equation? What do we get from these equations? Now, imagine that you have a tensile specimen made of certain materials. Okay, you stretch it, you deform it, but you deform it elastically. I start with something simple, elastic deformations. Okay, the amount of force that you need to deform the materials actually is needed to overcome two phenomena in the materials. First, when you deform the materials, you change the internal energy and you change the entropy, which means that the force that you apply is because you need to overcome the fact that you change the internal energy and you change the entropy of the materials. So there are two contributions of the resistance of materials, how difficult to deform the materials, because you need to change the internal energy of materials and you need to overcome the fact that you change the entropy in the materials. So the first term is called as energetic contributions to the elasticity of the materials. The second term is called as entropic contributions to the elasticity of materials. So now, here, what we get. Let's have a look. The first class of materials, metals, for instance. It is a crystalline materials. You have learned in the first year. If your tensile specimen made of metals and you look at the microstructure, it consists of regular structure, regular atoms. This is called as a crystal. You have learned FCC, BCC, HCP, and so on. Okay. So what happened is that now, remember, we are talking on the elastic deformations to make things easier. We have learned also in 2 weeks ago that elastic deformations in metals correspond to the stretching of atomic bonding without breaking it. So if I illustrate here between two atoms, between the two, it exists bond, atomic bond, which we illustrate in the form of spring. When you stretch it, then the spring elongated. When you compress it, the spring is compressed. Okay, so you just simply stretch the atomic bonding without breaking it. It is elastic deformations. So what happened when you stretch the atomic bonding? Basically, you change the energy, the change of internal energy. So you pull it one another per part or you compress it, you modify the internal energy. How about the entropy? Do we change the entropy by deforming elastically the crystalline materials? Well, the change in entropy will not be as significant as of internal energy, because you have learned entropy is certain measure of irregularities. Your materials remain well regular structure. You only disturb it a little. It is elastic deformation. So in the case of metals, which are crystalline materials, during elastic deformations, you only change the internal energy without changing the entropy. That's what happened from the thermodynamic standpoint of the deformations of crystalline materials. There is another class of materials where the microstructure is completely random. It's not like metals. It is called as amorphous materials. Examples are rubbers. Okay, so rubbers are amorphous materials. So you have learned also in material science. It consists of polymeric chains, random polymeric chains. So rubber is a certain class of polymer. So what happened during elastic deformation is that you simply change the conformation, the shape of the chain. So from highly coiled structure, irregular, to become highly aligned in certain directions. Okay, so you simply change the shape of the polymeric chain. So elastic deformation corresponds to uncoiling of highly coiled polymeric chains, which give rise to the change in entropy. Because entropy is measure of irregularity, disorder. Before deformations, it is highly disordered. After deformations, what you see is that the polymeric chains tend to align along directions of stretching. It becomes regular. So passing from high irregularity to low irregularity, it involves change of entropy. But it does not change much the internal energy because you do not stretch the covalent bonding in the polymeric chain. So atomic bond in the chain is not stretched. The internal energy is conserved. So you see two different extreme situations. In one case, when you deal with crystalline metals, the elastic deformations can be attributed entirely to change of internal energy. For the case of amorphous materials, like rubber, the elastic deformation can be attributed to the change of entropy. So two opposite cases. So with that, we can then conclude. If we are dealing with amorphous materials, such as ideal rubber, then the energetic contributions to elasticity is 0. In the case of crystalline materials, such as metals, then the entropy contributions is 0. So the elasticity in rubber is often called as entropic elasticity because the deformations is associated with the change of entropy only. While in metals, crystalline materials, then the elasticity can be attributed only to the change of internal energy. That is why it is called as energetic elasticity. So this is the basic foundations from the thermodynamic standpoint, which means that later on, because we want to develop the constitutive equations relating between stress and strain, if I put it in a simple way, then the stress is simply force over cross sections. And then the force that you have here is from thermodynamic, is simply the change of the free energy with respect to the deformations. In the case of metals, it comes entirely from the change of internal energy. In the case of rubber, ideal rubber, it comes entirely from the change of entropy. So here, when you stretch the materials, the internal energy increases. When you stretch the rubber, the entropy decreases, passing from high entropy to low entropy. So the final entropy is lower than the initial entropy. So the change between the two becomes negative. Negative times negative become positive. That is the reason why there is negative signs here, because ds over dl is negative. Okay, so you have decrease in the entropy when you deform rubber materials. So here, I think this is the last slide for today. So basic foundation is that the stress can be easily computed if the mathematical expression for Helmholtz free energy is provided. Thus, depending on the type of materials, constitutive modeling consists in finding suitable expressions of internal energy or entropy, which means that now here, easily you can calculate the stress in the case of metals if we know what is the mathematical functions of U. Once we know the mathematical functions of U, you simply derive with deformation, you get stress here. In the case of rubber materials which are amorphous, you need to know what is the expressions of entropy, mathematical expression of entropy, and how it changes with deformations, and then this will give you stress. So what I'm going to do in the next is that in lecture 4, we are going to learn linear elastic material response. We are going to deal with metals subjected to the stress below the yield strength. So here, where we need to define the expression for internal energy. This will be the focus of lecture 4. So we'll derive the stress strain equations by specifying what is the form of du, mathematical equations. So you will need to get used working with symbol, mathematical equation symbol, not number. Okay. And then in lecture 5, after that, we are focusing on certain class of materials, which is rubber, showing nonlinear elastic material response. And this is through entropy. Okay. So this is how we are going to learn starting from lecture 4 and lecture 5. So again, as I mentioned, a short lecture for today. So we have finished with the thermodynamics of deformations. And then we are going to start by considering the first material response next week. See how we can apply the theoretical aspect that we learned in deriving the quantitative equations for different types of material response. So, okay. Before we finish, I'd like to open for discussions if you have any questions. Please, if you have any questions, let me know.
Excuse me, doctor.
Yes.
I have a question about the test.
About?
Test. Do we have test like midterm test?
Yes, we have midterm test. Yes. Let me check again on the schedule and I will let you know. Yeah, I think I have already informed it, if I'm not mistaken, in the first class. Yeah.
Yes.
I'll check again. Yeah. Yes, we have midterm test. Yes.
Okay. Thank you.
Any other questions?
Doctor, I have a question. Doctor, if the structure of a material does not change, that means the entropy also does not change.
Hold on. Let me stop my voice.
Doctor, can you hear me? Hello, doctor.
Arunesh, I do not hear your voice, so probably you can type in the chat box, yeah, for your questions. I see also here Andre asked questions about chapter 2. Despite the increase in yield strength, the ultimate strength will no. So strength hardening will improve both the yield strength and tensile strength. Okay, so it's not only the yield strength, but also the ultimate strength or the tensile strength. Arunesh, because
Can you hear me now, doctor?
Okay, go ahead, please.
Yeah. So for change in entropy, there needs to be a change in the structure of the molecular structure.
You're gone. Your voice gone.
I'll try to type.
Yes, please type. Yeah. In between, in the meantime, any other questions, please?
Doctor, I have a question about hardening, isotropic hardening, and kinematic hardening. I mean, which application exactly they use them? Like they use isotropic and kinematic.
Which
How-
what? Sorry, the question, which what?
Which application exactly? Like construction or automobile?
Good. Okay. So this one, the kinematic hardenings obviously occur when there is plastic deformations, which means that it is crucial in the applications where we intentionally needs to deform plastically the metal. And the example that I have put in the just now I mentioned is in metal forming, for instance, forging. When you need to forge metals to form certain specific shape. For instance, if you look at connecting rod in the car, which connect between the piston to the crankshaft, it is manufactured by forging specifically. So you press it, you deform it plastically. You heat it, you press it, you deform it plastically. So what happened is that when you deform plastically the materials, again, as I mentioned just now, is that you introduce plastic deformation, you modify the microstructure. As a result, you alter the mechanical properties, including the yield strength. So depending on how you deform it plastically, for instance, if you deform it plastically in tensile, you will have modifications of the yield strength and tensile strength in tensile, and also you will have modification of the yield strength and compressive strength in compressions. So to put it in the simple word, in which applications it is in metal forming, for instance, in forging applications, manufacturing process, when you need to deform plastically your materials. Another example is when you need to form, for instance, the car frame. You need to bend it, for instance. You need to deform it plastically. So there you introduce plastic deformation, you modify the microstructure of the material, you modify the properties. Imagine that you have, for instance, also pipe system. In chemical industry, in petroleum industry, when you produce pipe, and then after that, what do you do if you want to make a pipe bend? You need to bend the pipe. And then there is a process where you need to deform it plastically, and at the same time, you apply heat. And when you deform plastically the materials, the part which undergoes plastic deformation, we have properties will be different from other part which does not undergo plastic deformations. So these are the example of applications involving plastic deformation where the notions of hardening is important. Yeah.
Thank you, Doctor.
Answering your questions.
Yes, Doctor.
So any kind of applications where the metals are intentionally deformed plastically. Yeah. You bend it, application to make a car frame, for instance, from the aluminum, from steel, you need to bend it. In the pipe systems, in the manufacturing process, such as forging, these are the applications involving plastic deformations. You deform plastically the metal, you alter the properties of materials, and this is something that you need to consider when designing the component. Yeah?
Thank you, Doctor.
Sure, no problem. And then let me read Arunesh. For change in entropy, there needs to be change in the molecular structure. For change, okay. Here's the thing. Yeah, I'm not sure whether I have fully understand the questions, but let me repeat something. Yeah, you start the thinking by imagining you have materials, and then you pull it. One materials made from metals, you pull it. Another materials made from rubber. Okay, so what happened is that when you pull it, when you deform it, what happened is that in rubber, the molecular chain change from the initial state, which is highly random, high entropy, to become highly aligned, low entropy, which means that you pass from high entropy state to low entropy state. There is a change of entropy. That is why the stress strain response is entirely because of change of entropy. Arunesh, is that answering your question, my answer? Okay, great, good. Okay, Ibrahim, with reference to isotopic kinematic hardening for industrial application in design material, do we have to consider through stress or engineering stress? Okay, that is a very good questions. Yeah, so engineering stress is usually only we use it to define certain properties of materials. So the stress and curve from which we obtain mechanical properties are engineering stress, engineering strain curve. Yeah, the elastic modulus, the yield strength, the tensile strengths are from engineering stress. But for the real design, okay, when we want to have real informations, then it is the true stress that we need to look at. Yeah, it is the true stress, because this reflects what really happened to the materials, including whether there is strengthening in the material. The strengthening cannot fully capture if we use engineering stress. So when we design, it is true stress that we need to use. Yeah. If you learn about finite elements, then we need to look at true stress. Any other questions? Okay, good. It's answered your questions, Ibrahim. Any other questions, please? This is still very conceptual discussions. If you have questions, theoretical part. Any questions? Again, be careful. If you work on industry, metal forming, manufacturing, where you deform plastically the metals, be careful, because you will modify the microstructure, you will modify the properties, which means that you modify the strength. If you imagine that you have initially circular bar, 1 meter circular bar, and then you bend it permanently, okay? So what happened is that at the location where it is bent, it undergo plastic deformation. So you have modification of microstructure locally there. You modify the properties locally around the bend. So you will see that the properties will become non-homogeneous. In certain part, the extreme left part and extreme right part, which you do not deform plastically, the property will remain the same. But around the bend area where it undergo plastic deformation, the microstructure will be different, the properties will be different. So the yield strength will be different from the rest. So you deal with heterogeneous materials. This is one of the examples that you need to be careful. Yeah? That when you deform plastically the materials, you alter the properties. If your plastic deformation is not uniform in your component, it means that the properties will not be uniform in your components. Some part will have higher yield strength, some part will have lower yield strength. Any last few questions probably before I close? I hope everything is clear, yeah? So as mechanical engineers, when you design for load-bearing capacity, which may involve different types of materials, metal, ceramic, and then rubber, then you have understood the basic principle behind the deformation of materials, how the stress strain characteristic. Yeah? So next week, we are going to look at the case for metals subjected to stress, but still below the yield strength, so the deformation is elastic. We are going to look at linear elastic material response. Okay. I will look at from two different approaches, from physical approach and also from phenomenological approach, and then how the example. So Hooke law basically is the example of materials model, constitutive equations to describe linear elastic material response. Okay. Well, if there is no other questions, then I will stop here. In the chat, I think there is no other questions. Okay, thank you very much. So I will see you next week. Okay. Have a nice day.
Okay, thank you, Doctor.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Thank you, Doctor.